אחר צהריים טובים לכולם. אני אעבור לאנגלית, don't worry. Today is my great pleasure to talk about AutoML and debate its potential. AutoML is one of the initiatives of our lab. We have quite a bunch of talented people that I'm very proud to work with on this topic. In this talk, I will share a portion of our work. We're also in a collaboration with Tel Aviv University on a subject matter. And part of the work I'm going to present was a teamwork with Professor Raja Giris and his students. As we all know, one second. As we all know, we heard a lot in the last sessions, 10 years ago, although neural network and deep learning already existed to some extent, we were mostly researching handcrafted algorithm. For example, we were designing feature extractor like SIFT, orbs, etc. In 2010, as we all know again, we witnessed a breakthrough in the field. Neural networks were efficiently utilized on a large dataset called ImageNet. I will refer to that milestone as AlexNet moment. By the way, in my figures, people represent human labor. Time has passed, and neural network became very popular in both research and industry. We have made progress in understanding and designing and training neural networks, and today we got wiser with Professor Tishby's maybe put some light on the black box. World-leading researchers in machine learning and computer vision have manually designed network architectures and have invented and approved learning schemes and policies. A lot of the progress can be sought of manual tuning of different kind of hyperparameters. AlexNet, VGG, Inception, ResNet, ResNext, Exception, DenseNet, CondenseNet. You can look at it as a big hyperparameter optimization of network architecture search. This is just a short list of neural network architectures used for computer vision alone. And there will also have been numerous attempts that failed. Excellent researchers have and still are working on this. Designing and training a fitting architecture per problem requires painstaking efforts. Yet, despite the leap in the many efforts invested in improving neural network architectures and learning processes, machine learning has yet to reach the scalability which would allow any business to apply AI easily. Even the largest, biggest corporates struggle to apply efficient machine learning techniques to new fields, as can be seen from the example of autonomous driving. Therefore, one of the goals of the industry today is to break this boundary. What I mean is that eventually we would like to enable businesses to simply define their problem, as in define the input and the output of the desired solution, and have machine learning fill in the blanks by itself. Serious attempts to achieve these goals are already in works. Some would say that more than 20 years already. These days, a subset of this field is being called AutoML. Lately, due to the advance of neural network methods, some companies even claim to have reached a stage where their AI is creating AI. It's not us. But the truth is that we're at the very beginning of this development. The dream is to enable anyone to upload a data and with a click of a button to get a state-of-the-art architecture. For example, you could upload a labeled images of, let's say, intestines patches, okay, what we saw earlier today. And the goal of AutoML is to give you the state-of-the-art model for classifying the images into the categories. For example, polyp or not polyp. Without asking anything from beyond the labeled images to train on. Obviously, we must do that with reasonable resources. For example, just one GPU running on for one day. This is supposedly one algorithm to rule them all and eliminates the need for months of skilled research. It isn't clear how to achieve that. I would like to repeat and maybe confess, I think maybe many in the room think the same. Neural architecture creation is a painstaking process. It involves first gathering a lot of data, which we saw is very important by Dr. L from Google. And then it mainly involves a selection of two families of hyperparameters. Hyperparameters related to the network architecture itself, and hyperparameters related to the network training process. With this understanding, the industry and the academic world are currently striving to discover how to automate the selection of this hyperparameter. A third method that is widely used today is transfer learning, in which a network, for example, well designed by human, is first trained on an extensive dataset, such as ImageNet, and then later tweaked with a new dataset or a new input-output configuration in order to support a new problem. Although this is a good direction, and is already widespread use, this method might be limited in performance and domain transformation. Niv, I know you're smiling there. Let us focus now on automated architecture search. The drawback of automated network architecture search is that it is a very difficult optimization problem. In some implementation, it could be a combinational optimization with more than 1 billion possibilities, which may require a full weight training for evaluation. These huge searches are extremely expensive, which is the reason currently a game, this entire topic is a game mainly for giants. For example, one work published in 2018 called the MebaNet required 3,150 GPU days in order to solve one classification problem. Therefore, existing solutions are strongly biased towards current human understanding of neural network structure, instead of searching for real architecture innovation instead. In other words, the most advanced solutions in use today heavily rely on human expertise to define how to decrease the full search space. For example, humans can limit the search space to architecture similar to those known to be successful. This combination of human expertise and machine learning techniques may yield a very efficient automatic method which solves well-defined problems in a matter of days. Researchers around the world have been analyzing the potential of this direction during the past few years, with promising work such as ENAS and DARTS. Well, we have not yet reached our AutoML moment, but I feel that we might be on the verge. Maybe in a few years we'll sit here and there will be a panel about AutoML, black magic, yes or not. If we reach this milestone, it could possibly change the role of data scientists as it is today. Now, after throwing such a bombastic sentence, let's be more concrete and look into the key idea behind one NAS method. One common approach is to limit the search space toward networks with repeated cells. For example, as shown on the left, you can choose an architecture with 2 repeated cells, normal cell and a reduction cell. NAS only optimizes the structure of these cells, and people refer to it as micro-search. On the right, you can see 2 types of inception cells. Inception V4 is a common leading neural network these days. On the left, you can see an animation of our evolving cell during our NAS search phase. An optimization algorithm is efficiently evolving the cell to best fit CIFAR10 dataset. Can you see the similarity? Of course, some layers and connection in the graph are chosen differently between left and right, otherwise I wouldn't be here, right? But the similarity is very high. The overall macro architecture is even more similar. This is because the search space was configured by experts to be like that. And yet, we can get a lot while saving a lot of very expensive human expert time. There's already few leading approaches for NAS, including various optimization techniques based on reinforcement learning, evolution algorithm, random search also, and gradient descent based. These approaches get state-of-the-art result and improve the performance of human design network, or at least on par. Yet, their main drawback is the computational complexity of the search process. One reason for the complexity is the search space being discrete, or partially discrete. Enters DARTS. Continuing the concrete example of microsearch that I explained before, a leading solution called differentiable network architecture search have suggested to relax the discrete search space into a continuum one using a linear mix of all suggested operation per node in a cell. In this case, for example, it learns the connection of a normal cell in a microsearch and eventually selects only the strong connections. Let's elaborate about this search process used in DARTS. Differentiable architecture search is composed of 2 phases. In the first, an optimization procedure computes possible weights and architecture connection, which are branches within those repeating cells. In the second phase, the weak connections are pruned out. Adding a bit of notation and process details to what I just explained, the training optimizes the parameter of the cell in an iterative manner for 50 epochs by way of example. Then the pruning removes the weak branches all at once. Darts yields architecture with excellent classification results, and therefore it has attracted a lot of attention lately. You can see a growing attention to AutoML in general. On the downside, it is somewhat wasteful in terms of search and train time, because it keeps computing all the connections and prunes the weak ones only at the end. Furthermore, the architecture it generates are close to accuracy, state-of-the-art accuracy, but slowly below. We believe this is due to the hard pruning, which lead to suboptimal results. To overcome this limitation, we propose a direct approach, which we called BARTS. Now, after Professor Shmuel lecture, I'm not sure if I'm saying BARTS or BARTS, you choose. I'll try with the BARTS. Our approach performs pruning during the search phase using branch annealing method. Just like darts, we optimize the parameter of the cell during the search phase. But differently from darts, we use temperature parameter to gradually remove the weak branches. I will not get into the mathematical details presented in this slide, but I can tell you that our annealing process is not heuristic, but rather based on Gibbs-Boltzmann distribution. I hope that you can read more later on. We're supposed to submit a paper for this ICCV. Let's rather see an illustration. Consider 5 architecture parameters, which are those branches, the multiplier of the branches, that together constitute a probability mass function. It is, they sum to 1 and they are positive. They are marked by dotted lines and forced to change as the temperatures cool down through the search epochs. As we cool the temperature in the Boltzmann equation, the strongest become stronger and the weak decay. This way we force the winner takes all during the search phase. Worth remembering that the network weights parameters, the actual network parameters, are trained synchronically. Thus, this annealing process facilitates a sync between the pruning process to the actual network convergence. I'm going to show you some results, which is quite interesting, at least in my opinion, and through which I'll try to answer the talk's topic. Does AutoML lead towards computer vision as a service? These tables compare accuracy achieved by microsearch on CIFAR10 benchmark. We look on 3 measures: a classification error, the number of parameters of the network, and the computation time, mainly the search phase. You can see that our BARTS outperforms all in accuracy, number of parameters, and search costs. These tables compare the accuracy of MicroNAS solution on the famous ImageNet benchmark, and also compare the network designed by human manually. The top 4 are the human-made architecture. The next 2, NASNet and MEBANet, which is machine-made, but required thousands of GPU days or hours. At the bottom, I showed the more reasonable NAS solution, DARTS, SNAS, and the last is our BARTS. You can see that our BARTS maintain the accuracy while reducing the search time to 1/8 of a day of a single GPU. Notice that the accuracy of some human design network, for example, MobileNet V2, is similar to what BARTS gives us. What can we learn from this? Consider that it took a lot of expert time to design MobileNet V2 architecture. We can deduce that a lot of expert label can be used more efficiently. Let's see more benchmarks. In this table, I show a result on 4 further classification datasets. Our BARTS reduces the search time significantly by orders of magnitude while either improving or maintaining the classification accuracy. Worth noticing that some cases, other methods supposedly outperform NAS solution. But in fact, these methods can also be related to AutoML. For example, gpipe takes a huge 557 megabyte net designed automatically by a MEBANet method. And AutoAugment automatically learns data augmentations. Let's recap. BARTS is a variation of DARTS that replaces the hard pruning at the end with annealing-based soft online pruning. It gives us the faster training and a cheaper classification accuracy. But we can do even better with a more solid theoretical approach. As Professor Tishby said, if you want to do something practical, you should start with a good theory, right? So we have been working on more principled way to training branches, which is based on prediction with expert advice theory. Due to lack of time, I'm sorry, I cannot get into the details. I will shortly mention that it includes a new optimizer. Yet, you can come and hear us in a few related talks that we aim to do in Israel in the topic in the near future. The outcome is more principled method, and with a better result. We still need to improve the high memory consumption and release some limitations that I showed you before derived from the human design framework, such as shifting to micro-search instead of micro-search. There is more work for us, which is good, right? We still need a job. So that being said, our alpha version of the entire AutoML solution actually reaches higher accuracy than BART's and our EGW. Since NAS is not the only part of the AutoML solution, we saw that data-related technology, and as I mentioned, like data mining and data collection is one important thing, but as I mentioned, transfer learning and HPO, hyperparameter optimization, data cleaning and mining, etc., are complementary and can be automated as well. What you see here, for example, is our internal dashboard, Don't Tell Jack Ma, which, for example, includes a confusion matrix. So here are two of my suggested takeaway messages. Consider the possibility that researcher will soon progress to develop and use AutoML method in order to automatically design and train neural networks, instead of doing that manually. Maybe you can see it as a similar process, maybe somehow similar to the shift that we all did, for using neural networks instead of the heuristic or maybe handcrafted feature extraction that was done before that. Consider the possibility that one day soon enough, the AutoML moment may come and computer vision as a service will arise. Okay, last thing, I'll switch to Hebrew. אז אנחנו כמעבדת innovation מאוד גאים היום לפתוח את שערינו, ואנחנו, לכל מי שיש לו איזושהי בעיית קלסיפיקציה, מוזמן לפנות אלינו למייל, ואנחנו נעשה איזושהי בחירה של חברות מהאינדסטרי, שיהיה מעניין לנו לשתף איתם פעולה, ואנחנו נהיה שמחים לשתף איתכם פעולה ולפתור לכם את הבעיות קלסיפיקציה. אז thank you very much, finish here.